So, jetzt haben wir erfahren, dass die Welt wahrscheinlich durch böse Copy-and-Paste-Fehler verursacht durch falsche Ratschläge auf auf Stack Overflow jetzt doch langsam besser wird. Also die Welt wird besser. Jetzt kehrt aber so ein bisschen gleich wieder die Ernüchterung ein, glaube ich, weil es dreht sich jetzt alles um PDF-Verschlüsselung. Dazu möchte ich ganz herzlich begrüßen Christian Mainka und Jens Müller von der Ruhr-Uni Bochum, die sich dem Thema, was sie schon seit einiger Zeit gewidmet haben, glaube ich. Ja.
Also
und wer verwendet denn PDF-Verschlüsselung und PDF-Signierung hier? Hä? Das BSI. Ich würde jetzt... Sonst denn jemand im Auditorium, traut sich niemand zu melden.
Anekdote am Rande, das BSI hat seinen Report, dass PDF-Verschlüsselung gewisse Flaws hat, als verschlüsseltes PDF verschickt. Ja.
Also ich bin jetzt mal besonders gespannt, ob die 128-Bit-Verschlüsselung auch irgendwie unsicher ist, aber das werdet ihr mir gleich hoffentlich erklären. Gut, also erstmal herzliches Willkommen und wir freuen uns auf den Vortrag.
Okay, so thank you for this warm introduction. Yeah, I'm Christian. This is Jens. We are researchers in Bochum, and I did not set up it completely. One thing is missing. Give me just a second. Ooh, where is it? It's missing. Yay. Okay, should work. Okay, yeah. How to break PDF security. This is a joint work with lots of people, with my colleagues Vladi and Martin and Jörg from Bochum, with Fabian and Sebastian from Münster, and with Carsten from Hackmanit. And yeah, as Dirk asked you, so I want to increase this question. So who of you uses PDFs in general? So, oh yeah, I think so. Mostly 80% do use PDFs, that's great. And who of you did buy anything on Amazon? Anyone? Did you get an invoice for it? Yeah, so this is roughly 50%. If you buy something on Amazon, at least in Germany, you get an invoice. If you open it with Adobe, you can see that it's digitally signed. And this is one part of our talk, so maybe you want to take this invoice and want to change the content so that it's digitally signed, as you can see here, yeah, signed by Amazon DE, everything is valid, and you want to change the invoice maybe into a refund. So in the next 40 minutes, we're going to present you how to break PDF signatures, and you will learn how to change your Christmas invoice into a big refund. Yeah? And then I will hand over to Jens, and he will show you how you can get the knowledge out of an encrypted PDF so that you can extract the plain text and read the content. Okay, so let's start with the basics. So the road to all attacks are paved with basics, so let's go on. So I think most of you have already opened a PDF, and the idea that Adobe had back then in 1993 was to introduce platform-independent and software-independent document format that should be able to encapsulate texts, images, and graphics. And since then, newer versions are released, so the latest version is 2.0, and they added lots of features. So now you can have forms in it, you can have 3D objects, of course we need them, you can have JavaScript, that's a great idea I think, and you can also have encryption and signatures. And this is heavily used by lots of companies. We will see where they are used for the encryption part when Jens is going to talk. But signatures, we heard it already, at least the BSI uses it very largely, and Amazon and other companies sign it for invoices. But before we come to signatures, let's talk about PDFs. So I have created this wonderful PDF for you. It's very simple, so you can see that there is a simple text, right? Hello world. If you are familiar with Adobe products, you can see even a little bit more. For example, you can see, well, there's one page. We are currently on page 1, and there is one page in total, so you have some more information. This is nothing new for you. I think most of you understand this clearly. But the surprising part begins when you take the same file and open it with a text editor. Then you receive something like this. Okay, this is very small, so let me zoom in into the upper part. And even if you don't know what a PDF is, you can imagine what it means, so you can get some information out of it. For example, you can see that there is something with pages, okay? And we can see that there is a count 1, so maybe this is the one page that we saw on the previous slide. And you can see even the text, hello world. So just opening it in a text editor reveals some information. Okay, so let's have a more detailed look into this, and I'm sorry, now the hard part begins. We are looking at the basics. Each PDF consists of 4 parts. And we have a header, we have a body, followed by a so-called cross-reference section, or XREF section for short, and then we have a trailer. And if you ever want to implement a PDF parser, or if you, like us, want to do some research and you open it in a text editor and want to read it, there is this main trick. Start reading it from the bottom to the top. Don't start at the top, start at the bottom. So let's have a look at the trailer. What is the trailer? So basically the trailer, as you can see down here, has some information. For example, there is some root 10, I come to this in a minute, and there is a start XREF and a number 275. And this number is basically a byte offset. So it's a pointer to some other position in the document. And this position is, you might imagine, the start of the XREF section. So at byte position 275, there is an XREF section. It looks like this. So basically an XREF section has some table look like. So there are, for example, in this case, we have different objects. The first object is with ID 0, and there are 5 entries in this PDF. Okay, so for example, if we look at the last one, then we have an object that has ID 5. Why is it 5? Okay, so we start counting at 0, 1, 2, 3, 4. So this is object 4 with generation number 0 because there are only zeros. It is currently in use, indicated by the N, and we again have some byte offsets. So for example, at byte offset 184, there is a pointer to somewhere else in the PDF. Okay, this brings us to the body. What is the body? This is the main interesting thing. So there are all the texts, all the headlines, the items, the images, the formulas, the JavaScript, everything is in the body. And everything is actually an object. So for each entry in this table, we have a reference to the actual object. And the references are also within the object. So for example, this catalog object, it's 10. This is the root object, which we had here. The root object references a pages object. Okay, and the pages object references itself some kits, so the actual page. And there we have a reference to the 40 object, which has the contents, so hello world in this case. Okay, this is the hard part. Then we have a header. It basically has a line which indicates which PDF version is used. So in this case, we use PDF version 1.4. Okay, for the attacks, we need one important feature. Maybe you know this use case. You have a PDF and you want to review it. You add some annotations, right? So you want to comment something or you want to highlight some text. And this is actually also an object. So you create new objects whenever you add an annotation. And now you might think that these objects are simply added to this body part. So there is a new object. This is not the case. So for PDFs, what they do is they append it at the end of the file. So you have some kind of revision, right? So this comment, for example, is right here in this body updates, and we have, because we have a body update, a new XREF section update, and because we have an XREF section update, we have an updated trailer. Okay, this is very interesting. How does it look technically? So technically we have this PDF here on the left-hand side, and then we add a new content. In this case, we do not add an annotation. With incremental saving, we can also change objects. So we changed the object for to a new revision for 1, and we change, for example, hello world to hello OWASP. So we change the text. This is also possible because we have a new body, we add a new xref section, and we add a new trailer. Okay, that's it. Now let's talk about PDF signatures. To make it clear, we have 2 different types of signatures. So maybe you have seen electronic signatures. This is basically an image of your subscription. So it does not add any cryptographic protection, right? It's just an image of your subscription added as an image into the PDF. And then we have digital signatures. So digital signatures add cryptographic protection. They try to achieve integrity protection, so that you cannot alter the text or the content of the PDF without invalidating the signature. This is indicated, for example, by the signature validation panel in Adobe. Other products have other validation panels, and there can be signature form fields, so a visually indication that it's signed. In this talk, we only talk about digital signatures, so about cryptographic protection. Okay, so how do we sign a PDF? Let's assume we have a simple PDF. It has a header, it has a body, an xref section, and a trailer, and we want to sign it. So what do? We take this and we use incremental saving. So actually we add a new body update, and this body update contains a signature object. There are more objects, but for the sake of simplicity, we just use the signature object. So there is some signature object. It contains a signature value, the algorithm, all the information. We look into details a little bit later. Okay, so all the information that are necessary are appended to the end of the file, and then we need a new updated xref section, and we need a new updated trailer. Okay, and that's the output. So we have a signed PDF. Okay, now we understand how to sign a PDF, and now let's have a look at how to attack actually PDFs. Before we talk about concrete attacks, let's have a look at goals and prerequisites. So what do we need for a successful attack? So let's assume we are an attacker. And as an attacker, we have access to a signed PDF. So for example, we got a contract signed by our boss via email, or we maybe just bought something on Amazon and we got a signed PDF. Okay, so what can we do with it? We take this invoice, for example, by Amazon, and we can change it, we can manipulate it. So we can open it with a notepad, we can flip some bits, edit some text, whatever we like. Okay, and afterwards, we send it to a victim, to a support guy at Amazon or wherever, whoever validates it. Okay, and we assume that this victim is is an expert in PDF signatures, and he opens it. And he tries to validate the signature. So what does he do first? He needs first to validate that the signature details are intact. So for a successful attack, we need first that there is no indication that the signature is invalid. Yeah, so it must look absolutely identically. And second, we need to change the content. So in this case, we change the invoice into a refund. So 2 conditions: signature details must be absolutely identically, and the content must be changed. Now let's do some attacks. The first attack is called incremental saving. As you might assume, we use the incremental saving feature, and basically we add some content trying to keep the signature valid. Okay, so let's assume we have a PDF, and let's assume it's digitally signed. This is a different application, so it looks a little bit different, but it's valid. Okay, and now we know this incremental saving feature, and we have seen that we can change the text, for example. So what would happen if we simply add an update to this file and change the content, like we do it in a regular incremental saving attack, in a regular incremental saving? In this case, we would send it to the victim, and it might look like this. So it might look like, well, the signature is valid, but the document has been updated. So this is not a valid attack according to our scenario, because you might guess, oh, something suspicious is happening there. There was an update. So why was there an update? We don't know. So this is not a successful attack. But maybe some viewers do not show this. And yeah, actually this was the case, for example, in LibreOffice Draw. So when you open it, it was basically this attack. And then we thought, okay, how do they detect that there has been an update? And what we did is basically we took the signed PDF and we just add a body update. So we did not up an xref table, we did not up update a trailer, we just appended some body update at the end of the file. And this is not a standard compliant PDF, but we don't need standard compliance, right? We just put it into a viewer and open it, and this is somehow similar to, for example, browsers who try to render invalid HTML. So they try to do their best. This is not standard compliant, but maybe I can show you what I think there should be. And this attack, for example, worked on different viewers, on PowerPDF and on PDF Studio. And systematically we tried different approaches. So for example, we took the PDF and we added a body update and a trailer, but we skipped the xref section. So the application tries to detect, is there an update? And it detects the update because there is a new xref section. Because we did not add an xref section, it did not detect that there has been an update. And yeah, it was valid, for example, in Nuance PDF, PDF Element, and PDF Editor. Yeah, and then we also had some very smart implementations. They said, okay, you are allowed to do an update, but only if there is a signature object contained in it. Okay, there must be a signature object, one signature object. So what we did is we took the original signature update body. So there was one valid signature. We copied it and just copied it in this update. So we duplicated it. And this was, for example, successful on Foxit Reader and on Master PDF. Okay, so we did a systematic evaluation and we took 22 different applications. These are the results for the incremental saving attack. So the applications range from Adobe products like Adobe Reader and so on up to LibreOffice, as I mentioned, PDF Element, Soda PDF. So everything that we found that was able to validate signatures across different operating systems. So most viewers were available on Windows, but there were also a few on Linux and on macOS. Okay, and as you can see here, half of them, so 22 applications, were vulnerable to incremental saving, or at least one variant of them. Okay, and then we had a different attack. So attack number 2 is signature wrapping. I remember my first OWASP was on 2012 in Munich, and there I was talking with Juraj Somorowski about XML, and we did some signature wrapping attacks on SAML in 2012. And this was the basic idea. So what we basically did is we took the idea from XML and want to hide the signed content somewhere else in the document. Well, this is the basic idea. If you know signature wrapping on XML, this is the same concept but now applied to PDFs. Okay, so what did we do? Now we have to look a little bit more detailed at signatures. Suppose we have this document and we sign it. And now we have a look into the signature object. In the signature object, there are some very important keys. First, there is a contents key. Basically, there is a PKCS7 blob which contains a signature value and certificate information. And we have a byte range. The byte range indicates which part of the PDF is signed. So in this case, we have a byte range which says, okay, we start at byte offset A, which is typically 0, and take the following B bytes. Then we have a gap, start again at byte offset C, and take the following D bytes. So as you can see here, the green part is the input for the hash function that is used to compute the signature. So we have a gap inside. And how can we now do a signature wrapping attack? We simply copy the file, and then we stretch it a little bit. So we move the signed part a little bit down. Okay. Then you might have seen that there are lots of zeros at the end of the contents entry, and we can simply remove it. So we have more room, we have more space for attacks. And this space is then used to add a new byte range key. So basically we need to change it a little bit because we moved the second part down, so we have to change the C position to a different position. So we simply change the byte offset. This is not part of the signature input, so we can simply add a new one. And in the remaining space, we can add new objects, we can change the text content, maybe we need some padding, and then we add a new xref table, which must be at the same position as the original one. This is due to some technical restrictions, but it's not a big deal. Okay, so this was an absolutely new attack variant. No one has done this on PDFs before, and it turns out that this is why it was very, very successful. So we could bypass the signature validation in 17 out of 22 different applications. Okay, and if you look at this table, you're maybe like me, so it looks very good, so it seems that all applications are somehow vulnerable to at least one attack, except for one application, right? So if you look in the upper part, you see that Adobe products are still not vulnerable. And this was somehow sad for us. So we were really, we wanted to break Adobe again. And yeah, then we thought again at OWASP 2012 and thought, okay, there was another attack on XML. So basically what we did, the most stupid attack that you can do is to strip out the signature, right? So you know it as signature exclusion or signature stripping. And this is of course working in PDFs, but then there is no validation that panel that indicates that there is a signature which is valid. But the basic idea remains the same. So we want to remove something out of the signature and let the validation logic say, well, everything is fine. So what did we do? We have again a look at the signature object, and we have this content and the byte range key. We cannot leave out the whole signature object because then we don't have a signature. So the expert might say, well, it should be signed, but there is no signature, there's something wrong. Okay, but what else can we do? Maybe we can just leave out one key. So let's just say we have a signature, but there is no signature value, there is no certificate. Yeah? Or maybe we say there is a contents key, but it does not have a value, or we set it to something strange. And this, for example, works on two viewers, on PDF element and PDF editor. And yeah, there's another key, there's this byte range, and we can do the same basically. We remove it, or we set it to some strange values, and basically this works on Adobe. So this is quite cool. The attack was successful on on 4 applications, so basically on Adobe products and on PDF element editor 6 Pro. I think they use the same engine somehow, so maybe this is the reason why both are vulnerable. Okay, and as you can see now, we have a very dangerous part. I want to do this in a demo. So let's try to do... Oh, this is not what I wanted. Oh no, what's happening here? Oh yeah, that looks better. So where is my... Okay, so I simply move some icons. Yep, perfect. Okay, so here we have a very simple PDF. Well, it's not so easy. And if we open this PDF, you can see, well, this is valid, there is hello world, it's signed, everything is fine, right? Okay, so now we take this file, open it with Notepad++, and let's say we want to change the content to, let's say hello OWASP. Okay, if we open it now again, it should be invalid, right? Because we changed some content, and yeah, it's invalid. That's bad. Okay, and now I will show you a simple trick. With just one character, we can bypass this. Just one simple character. Okay, so we go a little bit down and look for the byte range, because we heard that it's an interesting entry, and there it is. And now I simply remove the byte range. I comment it out with 1% character. Okay, let's save it, and now let's open it again. And whoa, it's valid. Hello OWASP, you see the new content, yeah, and you can see signature is valid. Okay, so I'm right in time. So just to conclude the signature part, out of 22 applications, 21 were vulnerable. There's only one that is not vulnerable. It is Adobe Reader 9 on Linux. So maybe if you use Linux and you look for Adobe, it's no longer supported. So at the time when we did the evaluation, it was still in the repositories, but then they removed it because there were some other issues like remote code execution and so on. So maybe it's not the best idea to use it. Okay, with this, I hand over to Jens. Just checking, it's working.
Perfect. So after Christian and others had a look at signatures, we thought, why not also looking at PDF encryption? Maybe it's worth having a look. Which resulted in the PDF exfiltration or PDFX attacks we published in November, I think. So what is PDFX? PDFX is one of those attacks that come with a logo. And also it's two novel attacks in PDF encryption, which I will present, or I will only present the first one, the easy one. So both of them were basically found by carefully studying the standard. Both of them are standard compatible attacks. One of them is based on flaws in the PDF data format, which allows for partially encrypted content, which is always bad if the data format allows partial encryption. We call this attack direct exfiltration. The other one is based on the actual crypto on flaws in the used block cipher modes of operation. We call this malleability gadgets. You may have heard about malleability gadgets. It was presented last year by Chris Dresen in the context of email encryption. So the second attack basically steals the attacks from attacks on PGP and SMIME and uses them on PDF. So I'm only presenting the first attack, the direct exfiltration. Okay, so this PDF thing, yes, it supports AES based on document encryption using either a symmetric password or certificates. And AES, come on, AES is pretty much secure, right? So basically, if someone breaks AES, the sky is falling anyway. So, and we thought maybe we can give up here, but we didn't yet want to give up. So we thought maybe they did something wrong, maybe some implementation issues, or maybe some other issues. How did they actually apply encryption and AES encryption in PDF? Let's maybe first answer the question, who actually uses PDF encryption? Well, that was the hardest part. So, for example, the Kreissparkasse Stade does. So it's very popular, and some other banks do. So basically what they do is they know that a lot of their customers, they cannot handle PGP and SMIME, and therefore what they do is they send you all their sensitive stuff as an unencrypted email with an encrypted PDF attachment, and then they send you the password over a second channel, such as SMS. Why not? And there's even some companies that allow you to do this directly within the email client that sell Outlook plugins to substitute PGP. Yeah, why not? And a lot of modern scanners, they allow you to directly encrypt scanned documents. For example, if you use the scan to email feature, this kind of makes sense. And yeah, in the end, there are some companies, there's a lot of companies and governments worldwide that actually use PDF encryption. For example, the Department of Justice. Okay, so it's definitely worth having a look at PDF encryption. Some people actually use it. Okay, so let's first define our attacker model. So we are both from academia, like a lot of you, so we need some formal attacker model. It's not so formal in this case, but okay. Assume Alice wants to send a document to Bob. She's going to encrypt that document because the communication channel is not trusted. So this could be email, for example. Or assume there's some kind of a shared cloud storage, and Alice first uploads the document and Bob later on downloads it. And the storage may be accessible by a third party, like by other users. So in such cases, you cannot rely on TLS. It makes totally sense to use end-to-end encryption, and PDF encryption is a logical candidate for this workflow. Okay, now what is our attacker allowed to do? So our attacker is an active man-in-the-middle attacker who can perform targeted modifications of the encrypted document, either in transit or at rest, relying on some storage. Like, for example, flipping some bits in the ciphertext, but also changing the structure of the actual document. Before the attacker relays that still encrypted but somewhat modified document to the intended receiver to Bob. So the usual workflow now is that Bob is going to open this document with his password, and the idea is that once Bob decrypts the document, opens it, the plain text is leaked to the attacker. We assume that it's a super strong password or even certificate-based encryption, so we cannot apply simple offline brute force attacks. This will not work. It's important to note that this is an active man-in-the-middle scenario, but the only reason why you use actually end-to-end encryption is that some malicious party in the middle may be assumed. So an attacker can somehow manipulate your data before forwarding it. Okay, so how does PDF encryption technically work? Let's first look at some PDF encryption basics, which then result in the direct exfiltration attacks, the first class of the attacks, which I'm going to introduce today. Okay, we have already seen a simplified document structure for PDF document, some header, some body, cross-reference section, and the trailer section. For our attacks, only the body is actually the relevant part. Let's now encrypt this very document and have a look at the result. It looks interesting, right? So actually not the whole document structure is encrypted. Only certain parts of the document are encrypted. So what happens is that some encrypt object is added here, which contains some values like, for example, which encryption scheme is to be used, let it be AES-256 or whatever, and some other values. And the only objects that are encrypted are the object streams that contain the actual displayed data, the actual displayed content of the document. Why is this? Let's have a look at the standard. So the PDF standard says that all strings and streams in a document are to be encrypted, but not all other object types, such as integers or Boolean values. Interesting. Why do they do this? They want to be efficient. So PDF files should be efficiently parsed, allow random access to all objects, even for encrypted files. What does that mean in practice? So in practice, this means basically that the whole document structure for encrypted PDF documents is actually unencrypted. Only strings and streams in a document are actually encrypted, which reveals a lot of unencrypted information to the attacker, like, for example, the number of pages, their size, the number of objects, if there's links, and a lot of more stuff. This is not a real problem because the actual content is not yet leaked to an offline attacker. But still, it looks fishy, right? Okay, can we do more? We thought, maybe let's look at the standard again, we thought. In 2003, PDF introduced crypt filters. They allow you to use a finer granularity for encryption within a PDF file. What does that mean? This means that not all contents of the document have to be encrypted. You can create a document where parts of the document are encrypted and other parts are not. There may be legitimate use cases for this. I don't know. It also means, of course, that each and every standard compliant PDF viewer must support partial encryption, which can be very dangerous. So in other words, an active man-in-the-middle attacker who can modify a document in transit, for example, can add and mix her own content with the encrypted content. And it's not only crypt filters. By carefully reading the standard, we found 18 different techniques to actually do so, to add our own unencrypted content to an otherwise encrypted document. So this allows for simple content overlay attacks. So maybe I can show you a demo. It's pre-recorded, so it should work. Okay. So you can see a super simple encrypted document that just says encrypted text. Let's open this document with a text editor. You can see there's some garbage. It's the encrypted part, and AES encryption is used. So we don't know what's in there. But we can add our own object number 6, and we define a crypt filter without any arguments, meaning that this content is actually not encrypted. Okay? And then we add this object number 6 to the contents of the document, save that file, and open it again in Adobe or each and every other view that handles PDF encryption. And we can see, oh, it's the wrong conference, yeah, you can see. But there should be something like OWASP. Okay, sorry, I didn't have time to record another video. Okay, but you see it's super easy to add new content for an attacker to an actually encrypted file. Okay, now you may say, fair enough, because the standard guarantees confidentiality, but not necessarily integrity of the document. And we only broke integrity, that's not yet an attack, right? So we thought, can we do more? Can we do some targeted manipulations? Can we, maybe using these techniques, somehow exfiltrate the plain text by doing some target modifications of the document structure? Maybe we can. Let's have a look at the standard again. So if you carefully read the specification, you will quickly spot possibilities to communicate with the outside world, like, for example, form actions. So similar to HTML, PDF also allows you to insert some data into a form, like in your Dienstreiseantrag, then you print it, then you sign it and handle it to the next department. But you can also click on some button and it's electronically submitted like HTML forms. Nobody uses it, but it's there. Oh, that sounds interesting. And what's even more interesting is that the value to be submitted can be a reference to any string or stream within the document, or hundreds of them. Wait, strings and streams, those are the only parts of the document that are actually encrypted, right? Okay, so our idea was then, let's do some social engineering, place some button overlaying the whole document, the user clicks in there, and then maybe everything is leaked, the plain text is leaked. And we thought, clicking buttons is lame. So let's consult the standard again. And then we saw, there's various options, like events in JavaScript that can trigger any action, like a submit form action once the document is opened, printed, closed, and so on. Okay, yeah, you see where it's going. Let's put this all together. So this is a minimalistic encrypted body of a PDF document with some encrypted data. What we can see here is we added some submit form action. The value is the object number 2, and the object number 2 is the encrypted data. And then we added in the third line an open action which automatically submits the form to the p.df server, which is the server of our attacker. Okay, and the idea is that once a viewer opens this file, decrypts it, the content is leaked. Now, this is not a theoretical issue. Let me show you a demo. Let's once again edit this encrypted file. And what we do now is we add an identity value for all strings in the document, meaning that only the streams in the document are to be encrypted and everything else is not encrypted, so we can easily add a lot of new content. And what we do here is we add a new open action that submits something to evil.xepsilon, and the value to submit it is the value number 4, and value number 4 is the actually encrypted content. Okay, let's save that file again, use Netcat or whatever to listen for incoming traffic on our server evil.xepsilon. Let's open that file again, for example, in Adobe, insert the password, and what we will see is that current versions of Adobe will ask us, do you want to submit data to evil.xepsilon? So once you click allow for any link or so on, for each other link it will be allowed, but still it requires some user interaction in Adobe to leak this encrypted part, the encrypted text. In a lot of other views, there's no user interaction because a lot of other views just submit the content. And also for Adobe, we found a little bit of a bypass because they, even before you click yes or no, they sent the first, so they sent the DNS request before you click yes or no for efficiency reasons. So what you can do is you can leak the first 250 bytes of the plain text, using a subdomain to your own attacker-controlled DNS server. Okay. And then there's some other options. So you have clickable links in PDF documents like in HTML. And once again, you can use this to leak data. However, it will open the browser, so it's not that silent like for some form submission. But you can also automatically trigger this so the user doesn't have to click. And of course, there's JavaScript where you can do the very same. I'm not going into details here. So you can access, using JavaScript, the decrypted parts and then leak them. So there's 3 variants of this attack, basically. Okay, so this was the easy attack. I call it easy because it's easy to explain. This one is the more complicated one, based on the evil attacks, based on CBC mode of operation, based on flipping some bits and thereby getting known plain text. So the takeaway here is that you can do the whole thing again by doing targeted manipulation to the unknown ciphertext, resulting in the same attacks in the resulting plain text. Okay, but I'm not going into details because it's yet another 20 minutes talk and because I suck at crypto. Okay, so let me come to an evaluation of those attacks. So we already had that virtual machine from Christian. That's great, so we didn't have to reset up it all. So we just installed some more viewers because some of them only support encryption and not signatures. So I think it's 1 or 2 more. And as you can see, all of them are vulnerable to at least one of those attacks. So we distinguish between attacks with user interaction and without user interaction. So for over half of the viewers, that's the full circle, there's no user interaction required at all. For some others, you have to either click somewhere within the document or even confirm some confirmation dialog that you want to open a link. But again, this should not result in your whole plain text being leaked. Okay, and there's some viewers actually on Linux and macOS that are pretty much secure because they do not allow you to submit forms, they do not support JavaScript, and they only support links, and it was a bit harder there. But still, they were vulnerable to vulnerability gadgets. Okay, let me quickly come to the countermeasures. So, yeah, signatures, yeah, they should actually prevent those attacks, right? Signatures, no. Digital signatures, first of all, they will not prevent you from actually opening the manipulated file, and then the plain text may already be leaked, right? Signatures are not encrypted, so you can simply strip them. They're mandatory. You can also sign under the attacker's identity again, so no. And yeah, last but not least, of course, Christian just showed how to forge signatures. So no, they will definitely not prevent this. Closing back channels. Yeah, that's a good idea anyway. So alone for privacy, it's not good that the creator of a document can target whoever opens the document and send some backchannel to the server. Yes, we should do that, but it's an 800-page standard. It's very complex, and we only scratch the surface. I think there are much more backchannels in PDF. So I don't know if this will be successful. Also, I'm not sure if we should remove legitimate functions where the user clicks to submit a form or to open a link, which can also then leak the ciphertext, or JavaScript. Yeah, okay, we should remove JavaScript. Yeah, that's true. Okay, what some modern viewers now do, they at least ask the user before connecting to a server. So that's how Apple patched it, or the attack I just showed, the direct exfiltration variant of the attack. So they ask you, hey, you're actually leaking, you may leak encrypted content, do you really want to do that? Google also changed in Chrome the auto submission of forms and some other things, but then we came with these crypto attacks, and then they said, okay, we give up. We stopped trying to fix the unfixable because that's not our department, it's a problem of the standard, kind of. Okay, yeah, what can you actually do? So as a developer, you should deprecate partial encryption. It's always bad if the data format allows to mix encrypted and unencrypted content. Until this is implemented, you can try to somehow do some mixed content policy for PDF and disallow access from unencrypted to encrypted parts. And for crypto, some other countermeasures are required. You need authenticated encryption, so modern crypto needs to be introduced into the PDF file format. Okay, So what did Adobe say? Yeah, Adobe said it has been escalated to the ISO working group on crypto and signatures and will be taken up in the next revision of the spec. Okay, we will see what happens. That sounds good. So let me come to a conclusion. So as a developer of a PDF consuming application, you want to be error tolerant, right? You want to support crippled files like HTML and so on. But on the other hand, those issues, this error tolerance also leads to a lot of problems with signatures, for example, and that may be problematic in a security context. Of course, we should disallow partial encryption. No specification should allow this. It's a bad idea. Also, the crypto should be updated. Last but not least, there's been some research on brute forcing PDF files and insecure features, but not that much research on actually how it's crypto applied in PDF. Okay, so we have some website, and if you have exploits for each and every of you found in the evaluation for both signatures and encryption. So if you're interested, you can test if this still work. Okay, thank you.
Ja, vielleicht nicht allzu viele Fragen. Eine Frage kann ich erlauben. Da, okay. In die Ecke geht man gerne.
So, last night on Twitter, Taylor Swift accidentally dropped another 0 day, which was that the iOS PDF would crash upon opening encrypted PDFs. Did you also encounter crashes when opening PDFs?
Actually, we had a lot of crashes, and we put them in a folder, crashes, and they didn't make it in the paper, but yeah. Also, we can't exploit crashes, but it's super easy to crash actually a PDF consumer application.
Why can you not exploit it?
We need your help, or the help of some other binary guys in the room. We are application layer dudes. That's why.
Okay, dann danke nochmal den Sprechern für Ihren schönen Vortrag.